In this video, we're going to go over 10 practice problems related to the basics of drawing Lewis structures and identifying and classifying chemical bonds. So I would encourage you to try these practice problems out on your own. Go ahead and pause the video. There's 10 practice problems in total. Here are the first 5. And here are the next 5 as well. So go ahead and pause the video, try these questions on your own, and then we're going to talk through the answers to these in a step-by-step fashion. Okay, so our first question asks us to identify the number of valence electrons that a carbon atom has. And sort of implied in this question is when you're just given an atom and it doesn't say whether it's a cation or an anion or neutral, you can assume that it's neutral. So here we're talking about a neutral carbon atom. And when thinking about numbers of valence electrons, it turns out that the periodic table is going to define for us how many valence electrons are present. In fact, depending on what column of the periodic table, also called a group, we're dealing with, that's going to tell us how many valence electrons there are. So all we have to do is, skipping the transition metals, find out where carbon is on the periodic table, and look in the corresponding group. That'll tell us how many valence electrons there are. And so pulling up my periodic table, I see that carbon lives here, and this is in column 1, 2, skip the transition metals, 3, 4. So that tells me that carbon has 4 valence electrons, which is in fact the correct answer. For problem 2, we're asked to draw a Lewis dot diagram for an aluminum plus. Now that plus sign means that aluminum has a positive charge. In other words, it has fewer electrons compared to a neutral atom. And the fact that it just has a positive instead of a 2 plus or a 3 plus tells us that it's missing 1 and exactly 1 electron. And so let's look at where neutral aluminum is on the periodic table. I see that it's located here, which means that neutral aluminum would have 3 valence electrons. But aluminum plus is going to lose an electron. And so how we're going to draw the Lewis dot diagram is we are going to draw 2 dots to represent the 2 valence electrons. Normally with Lewis dot diagrams, it doesn't totally matter where you put the dots, but traditionally we put them in a counterclockwise fashion and we try and space out the dots as much as possible. So that's why I put them at the left and or at the top and towards the right. You do want to indicate the positive charge to show that this is an aluminum plus cation, and so that's where I've got this positive sign. And then it's also best practice if you've got a lot of dots and plus signs and minus signs in your picture to put brackets around the dots to help clearly visually distinguish them. All right, question number 3, we're given a couple of pairs of atoms and asked which would form a polar covalent bond. And so the answer is, in chemistry, we typically describe 3 different types of bonding: non-polar covalent bonding, polar covalent bonding, and ionic bonding. And the difference between these is that we think about covalent bonding being electron sharing, whereas ionic bonding is considered to be more of an electron transfer type situation. And so to talk about what type of bonding we might see between 2 pairs of atoms, we have to be able to think about this in terms of electronegativity differences. And so ideally, we can quantitatively answer this question if we have a copy of a periodic table that has electronegativity values. In that case, we have a couple different cutoff ranges that we're going to use. Different textbooks will give different information. The textbook we're using this semester puts these cutoffs at 0.4 and at 1.8. And so what we're going to do is we're going to subtract the 2 different electronegativity values, and then we're going to place, based on the difference between those 2 values, the little vertical bars mean that we're taking an absolute value. That's going to tell us what type of bond we're dealing with. And so on the slide, I've gotten an example for a bond between an oxygen and another oxygen atom. In this case, oxygen has the same electronegativity as itself, and so the delta En, or the difference in electronegativity, is going to be 0. And that tells us that O2 is a non-polar covalent bond. So looking back at our question text, that helps us immediately eliminate a couple of these answers, because I don't need to know what electronegativity carbon has to know that a carbon-carbon bond is going to be non-polar covalent. So really, we're looking at these 3 other options, and if we use our periodic table and pull up the electronegativity values, we can see that carbon and hydrogen have relatively similar electronegativity values. The difference is 2.55 minus 2.20, which is a difference of 0.35. That makes this just below the cutoff for it being a polar covalent bond, and instead it's going to be nonpolar covalent because those values are so similar. Looking at, by contrast, our MgO bond, from our periodic table and our electronegativity values, we see that magnesium has a value of 1.31, pretty small. Oxygen has a value of 3.44. So you can do the math. The electronegativity value ends up being greater than 1.8, and so that tells us that magnesium and oxygen form an ionic bond. And so you can compute the electronegativity difference, but kind of by process of elimination, that means that hydrogen and chlorine do have probably a polar covalent bond. We can go ahead and double check. Chlorine's here, 3.16. Hydrogen's over here, 2.21. That gives me a difference of 0.96, which means that that one is the polar covalent bond. All right, next question. This asks us something about what it means for an atom to violate or to obey the octet rule. And so what the octet rule says is that atoms are supposed to be able to have exactly 8 electrons. We'll talk in a second about how hydrogen is a little bit different, but in general, between the atoms between the bonds that it shares with nearby atoms and any lone pairs that that atom might have by itself, we want to make sure that the total adds up to 8. Hydrogen's a little bit different because it's in the first period of the periodic table, so the version of the octet rule for hydrogen and helium is that they want to have 2 electrons instead. So starting with our first option A, carbon A, what I'm going to do is visually isolate those bonds that are close to the carbon atom, and I see that there's a total of 1, 2, 3, 4 bonds associated with this carbon atom. Each bond, each drawn line, corresponds to 2 electrons, so that means that carbon A has 8 electrons, which means that it follows the octet rule. Looking at carbon B, we can kind of do the same visual exercise, but now we see that carbon B has 5 bonds associated with it, which would be 10 electrons. And so for this reason, carbon B violates the octet rule. For this same reason, while carbon C does obey the octet rule, it's got 4 bonds, which translates to 8 electrons, we've got some problems with our oxygen atom. We see that it has 1, 2, 3, 4 bonds, but also 2 dots next to it. So that's also a total of 10 electrons and means that this oxygen atom is violating the octet rule. Then last but not least, with our hydrogens, we see that this hydrogen has 2 electrons associated with it. And so even though hydrogen has a duet rule instead of an octet rule, it turns out hydrogen is perfectly happy having 2 electrons. So it does not violate our rule. All right, moving right along to question number 5. Now we want to think about some situations in which atoms actually do violate the octet rule. And the terminology that's used here is incomplete octet, which means atoms that are going to be okay having less than 8 electrons. And so this is sort of a definitional question. It turns out that elements that are more towards the left of the periodic table are more okay having less than a full octet. And so in particular, you might have learned in your course that boron, aluminum, and beryllium are 3 really good examples of atoms that tend to have less than 8 electrons in their octet. And so both of those are ones that we're going to select. You also learned that there are a couple of elements on the periodic table that will never, under any circumstances, violate the octet rule. Carbon and fluorine are 2 examples of that. You also don't tend to see other period 2 elements, other than the ones I mentioned with the incomplete octets, ever violate the octet rule. And then period 3 elements, meaning elements that are in rows 3 and beyond of the periodic table, those do tend to violate the octet rule from time to time, but instead of having incomplete octets, less than 8 electrons, they tend to have expanded octets, meaning that they can accept more than 8 electrons in certain circumstances. For question 6, we're asked to draw a Lewis diagram for CH4. And so when it comes to drawing Lewis diagrams, we want to follow this step-by-step guide. And I'll tell you the first thing is to figure out which step-by-step guide you want to use, because it turns out we do Lewis dot diagrams differently for covalent compounds compared to ionic compounds. So the first thing we want to do is determine for the different elements that are present here, we've got carbon and hydrogen. Is this a covalent bond or an ionic bond? And we just did a practice example showing that carbon and hydrogen have very similar electronegativity values. So this is going to be a covalent compound, in which case we want to follow the steps for Lewis structures with covalent compounds. And in these steps, the first thing to do is to calculate the total number of valence electrons for the molecule. And in our particular case, that is going to be, we've got some hydrogens. Each hydrogen has one valence electron, but we've got to multiply that by the fact that there are 4 hydrogen atoms, and that is going to give us a total of 4 valence electrons. Carbon, we have, each carbon has 4 valence electrons, but there is going to be only 1 carbon, so that gives us 4 more electrons. Adding that all up, we get a total of 8 valence electrons that we need to put somewhere. The second step of drawing a Lewis dot diagram is that now that we've determined the total valence electron count, we want to determine what is the central atom and attach the remaining atoms around it. So here our options for the central atom is either carbon or hydrogen, but usually it's the less electronegative atom that should be placed in the center, but hydrogen is never placed in the center. So by process of elimination, here it's got to be carbon. So I place carbon in the center, I put the hydrogens around it, and I draw what's called a skeletal structure, meaning I place at least one and exactly one bond between each of the things that need to be connected to each other. Doing the math, each bond corresponds to 2 electrons, so that takes care of, in this case, looks like all 8 electrons have already been accounted for just by drawing this skeletal structure, and I have 0 electrons left over. We'll see in future examples what to do with when I have more electrons that are left over. But if you put in your skeletal structure and all the electrons are accounted for, it kind of means you're done with the molecule. And we can just double check and make sure that a good structure is one in which we have the correct number of valence electrons and where we make sure that every atom is obeying the octet rule, especially for the ones that have to obey the octet rule. So here I see that the carbon has 8 electrons, the hydrogens have 2 electrons, so we seem to be pretty good in this case. Okay, so let's talk about problem number 7, in which we're going to have to draw a molecule where we might have some extra electrons we have to contend with. And so drawing this structure, we're still going to follow the same steps. So the first thing we're going to do is identify, we've got 1 nitrogen, 1 oxygen. Nitrogen has 5 valence electrons, oxygen has 6. So this is going to give me a total of 11 valence electrons. So the first thing I'm going to do, and I'm going to draw my scratch work up towards the top of the screen, is I'm going to draw the skeletal structure, which gives me 1 bond between the nitrogen and the oxygen. 1 bond is 2 electrons, so I'll subtract that off, and it looks like I have 9 electrons that I need to still place on this molecule. And so typically what I do is I start by drawing these as lone pairs. So here's 2, 4, 6, 8, 9 electrons in total. And you can already see that this molecule is a little bit weird in that most molecules have an even number of electrons. But some molecules like this one have what's called an odd electron count. And I can promise you, if you have an odd electron count, there's going to be at least 1 atom that violates the octet rule. And that's going to be okay. If you have an odd electron compound, it'll typically be the less electronegative element that's going to suffer the penalty and have its octet rule violated. The next step in our process, though, says that once we try and put all the dots in the structure, we might have to readjust them. This is step 4, and redistribute the electrons by turning lone pairs into bonds or vice versa. So my current structure is not, you can see it's not quite the final answer, because while oxygen currently obeys the octet rule, the nitrogen doesn't. And so one way that I can fix this is I can take this lone pair, or one of the lone pairs that I have on oxygen, and form it into a double bond. And if I do that, you're going to end up with a structure that is our final answer. And double checking, oxygen still obeys the octet rule, and nitrogen, while it only has 7 electrons, is much better than the 5 electrons that it had to start off with. And so this is going to be the preferred structure for this particular molecule. All right. Question number 8 now asks us to draw a Lewis dot diagram for a slightly more complicated molecule, in this case SF5-. So when we're doing our arithmetic in step 1 to figure out what the total valence electron count is, we have to take into account the charge. Negative charges put extra electrons into our pool of electrons that we have to distribute. Positive charges take away electrons. And so when doing this particular molecule, we've got one sulfur atom. Sulfur has 6 valence electrons. Our fluorines each have 7 valence electrons, and there are 5 of those, which gives me 35 electrons. And then that negative charge is going to give me 1 extra electron to add to the total, for a total valence electron count of 42 electrons. Just like before, I'm going to start by placing and determining what my skeletal structure is. Here, sulfur is probably going to be the central atom because it is less electronegative than fluorine, and a lot of molecules, especially if it's all the same element, are just going to serve as outer atoms, and it's going to form kind of a wheel and spokes type picture. So I've got my 5 fluorines on the outside. And the last thing that I need to do is I need to distribute the remaining electrons. So in the final answer box, you can see that this ends up being the case, that I put 3 lone pairs on each of the fluorines, and 1 lone pair goes on the sulfur. And a lot of students will ask, how do you know there's an extra lone pair on the sulfur? And the answer is, one golden rule for Lewis structures is that your total always must add up to the total valence electron count. So I have to keep placing electrons until I run out of electrons. And this structure that I've got as the final answer has 42 electrons. If you took away this lone pair from sulfur, you wouldn't have 42 electrons. Fluorine will always obey the octet rule, so it's good that all of them are doing that. You can see here sulfur has an expanded octet, and that's okay because sulfur is in period 3 of the periodic table. All right, 2 more questions to go. First, we're going to draw one last Lewis structure, this time for magnesium oxide. And you'll notice this one in the final answer looks a lot different than the other ones we've talked about so far. And it's because, remember, we draw Lewis structures differently for ionic compounds than we do for covalent compounds. So if you calculate either the electronegativity difference, or if you notice that on our periodic table, magnesium comes from the left side of the periodic table, whereas oxygen comes from the right side of the periodic table. Either way, you can spot that this, in fact, is an ionic bond. And so we have a slightly different set of step-by-step guides for how we're going to deal with ionic bonding. Ionic bonds are transfer of electrons, so instead of drawing lines in between them, we're going to do an electron transfer process. And what this is going to look like is we're going to start with both atoms. And I like to, when I'm dealing with ionic compounds, draw the Lewis diagrams for the isolated atoms first. That would mean that oxygen is going to start off with 6 valence electrons, magnesium with 2, and then an electron transfer process is going to happen. So the magnesium is going to transfer its 2 valence electrons. It's going to lose them, and it's going to donate them to the oxygen atom. And so that's why you can see that in my final answer, magnesium has no dots next to it, showing that it has no more valence electrons, whereas oxygen has 8 dots, 8 valence electrons. And then like before, we use brackets so that we can indicate the charges on each of the ions without getting it kind of mushed up in between where the dots are. And so this is going to be our final answer, making sure you can see we do a very different style for ionic bonds, and you do need to watch out before drawing a Lewis dot diagram that you know if you're dealing with something that's ionic or something that's covalent. All right, so our last question that we want to go over is we've got a more complicated molecule. This is something that you might see in an organic chemistry class, and we at least at this point want to be able to fill in a skeletal structure with any of the lone pairs and bonds that we need to complete this molecule. And so there's 2 different ways to do this. One, you could go through the step-by-step guide and figure out how many valence electrons there are, subtract them off, and then use the remaining to put electrons on the outer atoms and then form multiple bonds as needed. I'm going to show you one way that you can do this kind of as a cheat code and helps me do these problems much more quickly, which is to recognize that for all of these atoms, especially because I know this is a neutral, like it has an even number of electrons if you add up the number of electrons, everything in this molecule is going to obey the octet rule because we've got hydrogens, oxygens, carbons, and nitrogens. And so all that I need to do is look at each atom and determine what's missing in order for it to obey the octet rule. And so what I can do is on each of these oxygens, I can place 2 lone pairs. That's going to allow it to obey the octet rule. And then each of my oxygens, well, an isolated oxygen atom would have 6 valence electrons. And so if we form a double bond with a carbon, that means that each of these atoms is kind of contributing proportional to how many valence electrons it has. And so that is going to help me spot that it's probably going to be for this oxygen atom 2 lone pairs and 2 bonds that are formed because oxygen starts off with 6 valence electrons, so it normally wants to form 2 bonds in order to get up to the octet rule. And since it only has one thing it's connected to, the only way that I can form 2 bonds with oxygen is to connect it twice to this carbon atom. Similarly, because carbon has 4 valence electrons, it normally wants to connect to 4 different things or have some lone pairs. And so the best way to get this carbon to do that is to form a double bond with oxygen. Looking over at this nitrogen, nitrogen likes to be bonded to 3 different things because it starts off with 5 valence electrons, so forming 3 bonds is the easiest way for it to get to obey the octet rule. And so that means that apparently what I'm missing is 1 lone pair on nitrogen in order to get it to obey the octet rule. So that's the quick way that I can do this problem. Again, if you like to go slower and you like to go more step by step, you can go through the full list of how to do your Lewis structure. It'll probably take you a little bit longer, but you can feel more confident in getting the right answer. And with that, those are all 10 questions from this pre-assessment. If any of these didn't make sense, you can totally come to office hours and we can go over this in more detail. Otherwise, good luck and hope you learned a little bit about Lewis structures and how to assign and classify different types of bonding.